So question 6. Explain why the energy needed to separate different elements within a compound is an indication of the strength of the bonding within that compound. Quite a wordy question, but essentially, why is the energy required to separate the chemical an indication of the strength of the bonds within that chemical? Well, the stronger the force holding the two chemicals together, the more energy required to overcome that force. Okay? Again, that's really intuitive. So for instance, if I had a very strong rope, and I told a friend of mine to grab the other end and try and tear the rope in half, if it was a very weak rope, not a very strong rope, we could do it, probably. Now, if it was, say, steel cable, we'd probably just hurt ourselves. There'd be no way we could break it. And you can see the amount of effort that we put in will be much higher for the steel than it would be for the weak string. Intuitively, that kind of makes sense. The more energy you have to put in, the stronger that thing should be. That's why the bond strength is, or the amount of energy we put in, is directly related to how strong the bonds are in that chemical. So mercury oxide, HgO, this one, can be easily decomposed by heating, whereas potassium oxide, which is K2O, cannot. Now explain. When I heat mercury oxide, I can get pure mercury out. So that it's also called quicksilver, that, the liquid metal. Now, if I try to heat potassium oxide, I may not even be able to do it on this planet with the technology that we have available. How come? Well, potassium is more active than mercury, so it forms stronger bonds with oxygen than mercury. So another way of thinking about it is mercury is more stable than potassium. Mercury may want to go back to its metal form, whereas potassium definitely doesn't want to go back to its metal form. Because mercury can be fine, it can be stable in its metal form, whereas potassium is not stable in its metal form. So it doesn't want to go back to a state where it's unstable. It doesn't want to break up this bond structure here. So therefore, more energy is needed by the method of heat transfer to break the bond between potassium and oxygen than between mercury and oxygen. So because the potassium is more reactive, then it will hold on to that oxygen as long as possible, meaning you have to put more energy in just to separate them. Okay? Whereas mercury may be fine, may want to be separated, it will break up if you apply enough heat. Okay? Describe the two major types of chemical bonds found in compounds. Covalent, so you've got covalent bonding, which is basically sharing of electrons between atoms. Two atoms, or more could be, share electrons so that they sort of trick each other into having 8 in their outside shells. There's ionic, so the other form is ionic. There's also metallic, but that doesn't really form compounds. So in ionic bonds, there's an electrostatic attraction between oppositely charged ions. So you've got positive ion here and negative ion here, and they just attract each other like opposite poles in a magnet. Like the North Pole and the South Pole kind of attract each other. They hold together by that force of attraction. Now these ions are formed when electrons are transferred from an electropositive atom to an electronegative one. Okay, so when an electron is given away by an electropositive atom, electropositive is just another word for not at all electronegative. It's pretty self-explanatory. It's just not electronegative. To a very electronegative, the electropositive one gives the electron away, and the electronegative one grabs the electron and forms an ion, and they both form positive and negative ions respectively. Okay? And then that obviously forces them to attract one another. So to boil water requires relatively little energy. However, to decompose hydrogen into decompose water into hydrogen and oxygen, it requires a lot more. So explain why this is so. When we boil water, we see that water boils very readily. I can put on the kettle and it will boil very quickly. But if I wanted to turn all of that water that I put in my kettle into hydrogen and oxygen, it won't happen anywhere near as fast or with the same amount of energy. So explain. So why are we doing it? So why is this happening? Well, to boil water, we only have to overcome the very weak intermolecular forces. So for instance, say I have my water molecule here and a neighboring water molecule here. There's some kind of force that holds these two together. Just because, water's a liquid and they will interact, so they'll tend to hold each other together a little bit. So in order to turn this into a gas, all I have to do is just separate that bond here. And that's very easy to do because you saw there's only a dotted line. It's a pretty tenuous link holding these two things together. By breaking that line, now they're free to move, and that's just like forming a gas. If I want to break this into hydrogen and oxygen, I have to break these ones, these solid lines here. And they're much more difficult to break, and thus it takes a lot more energy because they're much stronger. So when we decompose water, we have to overcome the strong covalent bonds in the substance. Now this is the reason why decomposing chemicals often takes more energy than simply boiling them. If we want to boil a chemical, it tends to take less energy than if we were to decompose them. So energy is required to separate components in a substance. In an ionic substance, what force has to be overcome in order to decompose? So when we want to decompose an ionic substance, what force are we actually overcoming? Well, in an ionic bond, there's an attraction between the negatively charged and positively charged ions. So there's a force of attraction between the two. Now that is analogous, or is very similar to, or can be thought about in the same way as north and south ends of a magnet. So when you have two magnets near each other, they either repel each other if they're the same, or they attract each other if they're different. So the same thing happens for electrically charged things. This force of attraction is very strong, and it's not easily overcome using heat. The force of attraction, or the electrostatic attraction, is the force that we're overcoming when we're dealing with ionic substances. So that concludes today's lesson on bonding and chemical energy. So we looked at what bond energy is and how chemical bonds relate to the energy within a particular substance. So in the future, we'll be looking at some first-hand investigations and dealing with different chemicals. So I look forward to seeing you at our next lesson.